And in this example, we're going to show a thermal simulation of a transformer, considering electromagnetic fields and the impact on the other components, as well as the thermal management of it. In order to do that, we're going to use the SimCenter FLOEFD with the Flow Analysis tab, and we're going to start the wizard to create a new project. We can type in a name such as test, and then we have to specify our unit system, such as, for example, temperature as being in Celsius, or we have our geometry characteristic as the angle being in degree instead of radian, because we need to specify the phase shift in the individual coils. Then we can set if it's an internal or external analysis. Of course, we want to use an external analysis because we have natural convection on the outside and there's no internal fluid volume in this model. We want to consider conduction, as heat conduction in the coil will be important. And of course, electromagnetics with a frequency of 60 Hz. Now, the radiation is important because we're going to reach quite a temperature. And we also need the gravity for achieving a natural convection. At this moment, the gravity points in the wrong direction, so we have to change that to minus y direction and set the other one to 0. Now we have the right direction of the gravity vector, and we can go to the next step. Here we need to select our fluid. We're going to use an air-cooled transformer, and in the next step we have to select then the material, the default material. Now, since most of the components are these copper coils, we're going to use those as a default material, and we're going to select the electromagnetic material, and here under common used materials we find the copper material. This is now the default material for everything except if we define anything different. We can skip the next two steps, as we will leave it with the default. And you can now see there's a larger computational domain for an external analysis. And we can easily change that by clicking on the computational domain and then simply drag these arrows. If you hit the Shift key, you can drag both sides at the same time. Also from the top and bottom. And if we rotate to the other side, we can also reduce that size here. Now the computational domain is already much smaller, and if we look in the detailed setting of the computational domain, you can also see that there is an EM domain for electromagnetic simulation. This will be left on auto. Good. Now we can hide the computational domain because it's much easier to handle the model this way. Now, as a different material, we need to define an iron core for this component. And for that, we're going to use the solid material setting, simply select the component, and select the right material from the database. Again, we're going to use electromagnetic materials because we want to consider the electromagnetic impact onto the material as being iron losses. And the other materials don't have these properties. So here we're going to use the non-oriented AISI silicon steel material, and we're using the M1924GA. And clicking OK, material is defined. Now, we also need to specify the coil power, and for that we have our electrical source. We can specify AC current and AC voltage because we're considering alternating current in order to generate a magnetic field. And for that, we're going to use 5000 volts on a 0 degree phase shift. 60 Hz was already predefined, and we can specify the number of stranded coils, which will be 180 for the primary coil. We're not going to manually specify the strand area, so we're going to deactivate that part, but we have to specify the coil and in which direction the flow goes. In order to do that, we're going to use the body selection, and we're going to shift this rectangle in the other plane and then move it over here. Now you can see currently it cuts through both parts of the coil, which would cause counterflow in the current, which we cannot use. And therefore we are going to change the rectangle to only have one part in it and create a circular flow of the current. So with that we can accept this, and we can specify the same goal, the same boundary conditions also for the other coils. Doing that for the second only briefly. At this point, picking again the second coil, flipping the rectangle and resizing it so we only use the one side of the coil for the flow. We're only going to also going to choose 5000 volt, but here we need to change it to a minus 120 degree phase shift. Again, stranded coils with 180 coils or strands, and deactivating the strand area. With that, we have the second coil already defined. The third coil would basically be exactly the same, except for the phase shift being minus 240 degree. Now, we also need the secondary coils, and for those we're going to use 0 voltage, and we don't have to change the phase at this point. We also need to change the stranded coils to being 1200 strands, and again no stranded area. We're choosing 1200 because we actually want to transfer or convert the voltage from a lower to a higher, or from a higher to a lower voltage. And for that we need to have a difference in the stranded coil number. And specifying again the coil, flipping the rectangle, the same procedure as the last time. You can also choose the other side, but then we would have the counterflow. So you could also then move the coil this way to have it on the other side. Click in on OK, and the boundary condition is applied. Now, in order to get also some results at the end, and accurate results, we want to use goals. Global goals can be used in the overall simulation. For that, we can use parameters such as static pressure, the fluid temperature, in average. We want to maybe use goals such as ohmic losses, iron losses, and magnetic losses. Ohmic losses caused due to current flow, iron losses caused to magnetic interference with the material, and electromagnetic losses being both of them together. We can also pick other goals, but at this point this is enough for us. We could also, for example, specify volume goals onto the individual coils to actually know, for example, what are their specific iron losses or ohmic losses. Since we're having flow going through here, there will be only ohmic losses, and we can also, for example, look at the temperature of the solid at this point, for example, the maximum temperature of that coil or average temperature, and define these as goals as well. So defining these goals on all the individual components which are important for us gives us at the end information about how hot directly these coils are, as well as they're used for the conversion. So making sure that the results are converged and accurate. At this point, of course, the electromagnetic simulation will not be done on an iterative way by each iteration. So we can actually set this in the solving settings of the calculation control options by specifying how big the period is, so every 25 iterations, and we only maybe want to use it twice. At the very beginning, because we need a heat source for the thermal simulation, so the electromagnetic simulation is done first, and then after 25 iterations there will be another one in order to update the electromagnetic simulation based on temperature changes in the material, which will impact the electromagnetic properties of the material. So if the model is fully set up, we can run the simulation. Of course, we have already done that, and there are even more boundary conditions and more goals applied to it. So we can switch to the fully calculated model at this point, and you can see there is a local mesh as well on the coils for the fluid, and a region also for the fluid, because we have thinner channels between the coils that we want to resolve for the fluid flow. And if we load the results, we can visualize various parameters in our model, from CFD to magnetic fields. So at this point, for example, if we want to show the magnetic flux density, we can see that in a cut plot, and it's much bigger on the between the coils than on the outside, but we can also visualize magnetic flux with this streamline type of plot, where you can see the flow field, the magnetic field lines. We can visualize also the temperature. You can see nicely the plume from the natural convection moving the hot temperature up. And if we are going to show also some surface plots, we can visualize, for example, the mesh on the surface. This is the electromagnetic mesh. You can see on the copper on the iron core. You can see a coarser mesh. Then on the copper coils, because we have specified a local mesh on the copper coils. We can also visualize the iron loss, and if I hide the core, you can see the visualization of these losses on the core. Again, hottest on the inside, we reach around 1300 watt per cubic meter on the inside, and much lower losses on the outside. Looking at the temperature on the core, you can see it reaches 141 degrees on the inside and about 51 degrees at the colder positions here on the outside of the core. And of course, we can also visualize the streamlines and animate them to show the natural convection in our model. If you want to know how much losses there were on the components, we can, for example, show the surface radiation onto the core, so how much the hot copper coils were radiating onto that surface, as well as, for example, our iron losses of the core and our ohmic losses onto the copper coils. So clearly you can see there's a lot of energy being transferred either from the magnetic field onto the core, which you can see here with the iron losses, or also through radiation and convection near the core from the copper coils as it passes through onto the core, as well as radiate from the copper coils onto the core. So with this type of simulation, you can couple electromagnetic simulation with fluid flow simulation, all within one tool, within one solver run, and running on an iterative base. You don't have to do iteration by iteration, because the electromagnetic changes are considered much faster than even transient CFD simulations. And therefore, these type of iterative approaches only work on several iteration bases, like 25 as we have set it in this model.